Hey guys, this is Guided Practice 16. This is 7.8, our improper integrals. So in the first one, we've got an improper integral because we have an infinity in that upper bound. So we solve that by replacing our upper bound with a t and taking the limit as t goes to infinity of sine squared x dx. Okay, sine squared x dx, this is your trig integral. So we're going to use our identities. It's an even power, so we're going to use our 1 minus cosine 2x all over 2 dx. That's going to give me the limit as t goes to infinity of 1/2 times x minus 1/2 sine 2x from 0 to t. And the limit as t goes to infinity of 1/2 times, when you plug in t, you get t minus 1/2 sine 2t minus, when you plug in 0, that's 0 minus 0, right? So that's all 0. So then you're taking the limit as t goes to infinity of 1/2 t minus 1/4 sine 2t. Okay, and then when you plug in infinity, this becomes infinity. And then you have minus an integral that does not exist. So in any case, this one is going to diverge because we do get something that is infinite, right? Sine 2t is bounded. So that one's going to oscillate between 1 and -1. And this one's going to, the first 1/2 t goes to infinity. And therefore, it's going to diverge, okay? Number 2, from 0 to 2 of z squared ln of z. There's no infinity in this one, but we know that the natural log does not exist at 0. So we're going to make this the limit as t goes to 0 of t to 2 of z squared ln z dz. This is the limit as t goes to 0 of, now we've got to integrate z squared ln z. So this is by parts because you're multiplying two functions and one of them is an ln. So my u is going to be ln of z and du is 1 over z. My dv is z squared and the antiderivative there is 1/3 z cubed. So this is going to become u times v, which is the 1/3 z cubed ln z. Minus the integral of 1/3 z squared. And I'll put my boundaries back on at the end. So this is the limit as t goes to 0 of 1/3 z cubed ln z minus 1/9 z cubed evaluated from 0 to t. Okay, so now I can plug in my t and my 0. Oh, sorry. Whoa, hold on. Back the train up here. So I put this in the wrong spot. Let me fix my boundaries. This is going from t to 2. That way when I plug in 2, I have the net limit as t goes to 0 of. When I plug in 2, that's 8 over 3 times the natural log of 2 minus 8/9. Minus, when you plug in t, that's 1/3 z cubed. Oops, hold on. Put that in the wrong spot. It goes over here. 1/3 z cubed. Sorry, t cubed. We're plugging in t here. 1/3 t cubed natural log of t minus 1/9 t cubed. And now we're letting t go to 0. So this first term is just a constant. So this is 8/3 natural log of 2 minus 8 over 9. And then minus, you're taking the limit as t goes to 0. And this is a 0 times infinity. So we got to do a little bit of extra work here. This last term, the limit's going to be 0, right? But what about this one? So the 1/3 is fine. And we need to know what is the limit. And I'm going to move over here to the side. We need the limit as t goes to 0 of t cubed ln t. Right? If you plug in the 0, it's going to give you 0 times negative infinity, which is one of our indeterminate forms. So what we need to do here is move the t down to the bottom. So this is the limit as t goes to 0 of ln t over t to the negative 3. And then we have something that's infinity over infinity, or negative infinity over infinity. And we are going to be able to use our L'Hopital's rule. So by L'Hopital's rule, this is the limit as t goes to 0 of 1 over t times negative 3t to the negative 4th. If you simplify that, this is, let's see, negative 1/3 was the number. And I have, this is really t to the negative 1 over t to the negative 4 is t cubed. And when you plug in 0, you get 0. Okay, so this term is actually 0. And that means that we get 8/3, the natural log of 2, minus 8 over 9 as our value. So this one is convergent. So sometimes your limits are very straightforward, and other times you're going to have to work for the value. Okay, number 3, we've got the integral from 1 to infinity, right? So that's going to be a point where it's discontinuous. Note that you have an x plus 1 in the denominator, so you've also got a discontinuity at negative 1. But that's not in our interval, so I don't have to worry about that. Also note here that I have an n here, but that n is greater than or equal to 2. And we'll see how that plays out in a second. So to compensate for that infinity, we're going to take the limit as t goes to infinity of the integral from 1 to t of 1 over, and I'm going to rewrite this right away as x plus 1 to the negative n. As long as our n is not 1, then I don't have to worry about it being a natural log. So I'm just going to be adding 1 to my exponent. In this case, keep in mind that our n is greater than or equal to 2. Okay, so dx. So how do I find the antiderivative here? So you could baby use up here if you like. And that's going to give you the integral of just u to the negative n du, right? And so how do we handle that n? Well, we know that that n is at least 2. So if you had, let's pretend you had u to the negative 2. Then you would add 1 and you get u to the negative 1. And you would end up with over negative 1, right? So what we're going to do, if you had something larger than that, you'd end up with u to the negative something over something, right? So I'm going to have a negative exponent for sure because my n is greater than 2. So what this comes up to be is if it's just a plain old n, then we get u to the negative n minus plus 1, right? We're adding 1 to our exponent over that new exponent, which is negative n plus 1. So that's what our derivative is, that's what our antiderivative is, except we're going to plug our x plus 1 back in. So this is x plus 1 to the negative n plus 1 all over negative n plus 1. And we're going to evaluate from 1 to t. Okay, so that means that we get the limit as t goes to infinity of t plus 1. And I'm actually going to move it down to the bottom now so that we can kind of see what's happening. So 1 over negative n plus 1, that's just a constant. And then you're going to have 1 over t plus 1 to the positive n minus 1. And then when you plug in 1, you have the negative 1 over negative n plus 1. And then when you plug in 1, you get 2 to the negative n plus 1. Okay, so now what happens with the t's? So the second piece, this piece over here, that's just a number, right? And is a number that we don't know what it is, but we know it's greater than or equal to 2. And 2 to the negative n plus 1 is just a power of 2. So that's a number that all stays. So the question is, what happens with this first term right here? So the 1 over, that negative keeps throwing me off, 1 over negative n plus 1 stays. That's just a number. And then you're plugging in infinity down there for t. So you're taking t plus 1, so that's infinity plus 1, to a power that is going to be at least 1. So you're going to get at least a 1 over infinity here. And that 1 over infinity is going to go to 0. And so your limit value, your integral value is negative 1 over negative n plus 1, 2 to the negative n plus 1. And that's your final answer. So this one actually is convergent. Okay. Okay, now, same question here for number 4. Is this our last one? Yeah, it is. Okay, our last one here is the same question, only now we're going to let our exponent be less than or equal to 2. So we've got to be a little bit careful here. So the first thing we're going to deal with is that infinity. So this is the limit as t goes to infinity, integral from 1 to t of x plus 1 to the negative n dx. Okay, so we got to think about what's going on here. Okay, so n could be anything less than or equal to 2. So n could be 2, n could be 1, n could be 0, and n can be negative. Okay. So the only one of these that's going to be different is going to be this one here. Okay. So the special case for when n is 1, we get a natural log, right? So we're going to have to do that one separately. So let's think about this and how we integrate it. So for n equals 2, let's think about that one for a second. This is the limit as t goes to infinity of x plus 1 to the negative 2 dx, integral from 1 to t. And that's going to be the limit as t goes to infinity of x plus 1 to the negative 1 over negative 1, evaluated from 1 to t. So this is exactly what we had in the last one. So t goes to infinity, and you get negative 1 over t plus 1 minus 1/2, minus a negative 1/2, which is plus 1/2. And when you send to t to infinity, this becomes negative 1 over infinity plus 1/2. So that's 1/2, and it's convergent. So that's fine. Okay. What happens when n is equal to 1? If n is equal to 1, we get the limit as t goes to infinity of the integral from 0 to t of 1 over x plus 1 dx. In that case, this is the limit as t goes to infinity of natural log of x plus 1 from 0 to t. That's going to give you the limit as t goes to infinity of the natural log of t plus 1 minus the natural log of 1, which we know is 0. And we've done this one before. We know that the limit here is going to be negative infinity, because when you let t go to infinity, positive infinity. When you let t go to infinity, the natural log goes to infinity. So this one diverges. Okay, what happens when n is equal to 1? 0. It's the next one, right? We did 2, 1, 0. Okay. So we have the limit as t goes to infinity, integral from 0 to t of just 1 dx, right? Because when you have a power that is 0, it becomes 1. And that's going to be the limit as t goes to infinity of x from 0 to t, which is just the limit as t goes to infinity of t, which is infinity, so it diverges. Oh, wait, didn't want to do that. Add in some extra space. Okay. Then what happens if it's negative? So the limit, so if n is equal to negative 1, then you have the limit as t goes to infinity, integral from 0 to t of x plus 1 to the positive 1, right? Negative n, and n is negative, makes it positive, dx. So this is going to be the limit as t goes to infinity of x plus 1 squared over 2 from 0 to t. And so that's going to give you something that is t plus 1 over 2 squared minus 1/2. And now when you've got a polynomial that sits here, right? And that's going to give you infinity every time. So when you're plugging in infinity here, this is infinity plus 1 over 2 squared minus 1/2 is going to be infinity. And that's going to be true for any number that's also less than -1, right? Because it's negative, that makes it something that's going to become a positive power. So what happens is that notice that the only one that converges is when n equals 2, right? And we knew that from up above because we had this one was greater than or equal to 2, and we knew that that converged. But down here, 2 converges, but everything else diverges, okay? So we checked a couple of cases.